Welcome to today's episode where we break down YouTube. You've tapped this button maybe 100,000 times. You never think about what's behind it. You just press play and it plays. But behind that one red button is one of the largest machines humans have ever built. And today we're going to pull it apart piece by piece and see what's actually inside. Let's start with one number because it sets up everything else. Every single minute, more than 500 hours of video get uploaded to YouTube. Not per day, per minute. So in the time it takes you to watch this one sentence, another few hundred hours just landed waiting to be processed. Nobody sits and watches those. A machine has to, and it has to do it forever without ever falling behind. But uploading is the small half of the story. That one video, once it's up, might get watched a billion times by people on every continent, on every kind of connection, all at once. So the traffic going in is a trickle and the traffic going out is a flood. Roughly 1,000 times more data leaves YouTube than enters it. Hold on to that ratio because almost every strange decision in this system is YouTube answering the same question. How do you write something once and read it a billion times? So before we open it up, let's agree on the job. 4 things really. It has to accept video from anyone, anywhere, on any connection. It has to transform that raw file into something every device can actually play. It has to deliver it instantly to millions at once. And it has to do all of that while things are constantly breaking underneath it. Because at this size, something is always broken. The trick isn't to never fail, it's to fail quietly and keep playing. Here's the whole thing at once, and I want you to really sit with the shape of it. Because everything else in this episode is just a close-up of one corner of this map. There are 3 separate journeys through YouTube. The first is the right path. This is the rare, expensive one. A creator uploads a video, it lands at Ingest, gets dropped into a job queue, exploded by the transcode fleet into every format, and finally written to storage. That whole chain fires maybe once per video. The second journey is the read path, and it runs in the opposite direction. A viewer presses play, the request hits a nearby cache first, then a regional cache, and only reaches the origin if both miss. That path fires billions of times a day. And the third is the discovery path, search and recommendations, which doesn't move the video at all. It just decides which videos IDs you get and hands them to the read path. Now here's the key. All 3 of those journeys lean on one shared spine underneath. The metadata layer that remembers what every video is, who made it, how many views it has, and where its bytes physically live. Vitess for the relational details, Bigtable for the counts, Spanner for anything involving money. Get this one picture in your head. 3 paths, 1 spine, and the rest of the episode is just us lighting up one road at a time. We'll follow a single video the whole way, from a creator's phone in Mumbai to a screen on another continent. Now let's zoom into that middle layer, because the split between reading and writing is the single most important design decision in the whole system. And once you see it, you can't unsee it. Every single request, an upload, a search, a play, comes in through one front door, the API gateway. And immediately, the traffic forks into 2 completely different worlds. On the right side, you've got the upload service, the job queue, the transcode fleet. This work is slow, it's heavy, it's expensive. A single 4K video can take minutes of compute across a whole fleet of machines. But it only happens once, when something new arrives. On the read side, you've got playback, discovery, and the counters. This work has to be the opposite. Instant and constant, running millions of times a second. So how do the read services stay fast? They almost never touch the real database. A view count, a video's manifest, your home feed, those come straight out of an in-memory cache that sits in front of everything. The database only gets bothered on a cache miss, which is the one long trip in this whole picture. same front door, two opposite kinds of traffic. One rare and expensive, one constant and cheap. And they only ever meet down at the shared data layer. First problem, and it's one every Indian phone user knows in their bones. You're uploading on mobile data, the bar crawls up to 80%, and then the signal drops. On a naive system, you'd start again from zero. YouTube refuses to do that. The upload is sliced into small chunks, and each chunk checks in as it lands. So when the connection dies and comes back, the phone asks a simple question: where did we get to? And the server says, you're good up to 80%, keep going from there. You never resend what already arrived. Once the whole file is in, YouTube keeps the original untouched, the pristine master copy, sometimes called the mezzanine. Everything you'll ever watch gets built from this one source of truth. Now the interesting part begins, and it's the heart of the whole machine. That one file you uploaded is useless to most of the world as is. Someone's on an 8K TV, someone's on a cracked phone on a train, someone's on hotel Wi-Fi that can barely hold 240p. They can't all play the same file. So YouTube takes your single master and explodes it into a whole ladder of versions, every resolution from 144p up to 4K and beyond. And inside each of those, multiple compression formats. But here's the clever move. A 2-hour movie in 4K would take forever to encode on one machine. So it doesn't. YouTube chops the video into short segments, hands them out to a whole fleet of machines that encode them all at the same time, then stitches them back into one smooth stream. A job that would take hours on one computer finishes in minutes across many. Now scale that up. 500 hours every minute, each one exploding into dozens of encodes. And some of those formats are brutally expensive to compute. For a while, YouTube ran all of this on ordinary processors and it simply couldn't keep up. So they did something most companies never do. They designed their own chip. It's called the Argos VCU, built for one job only: transcoding video. And it did that job somewhere between 20 and 33 times more efficiently than the servers it replaced. And YouTube doesn't give every video the full treatment. A family clip watched 12 times gets the cheap encode. A T-series music video headed for 100 million views earns the expensive one, because the bandwidth you save gets multiplied across every single play. So now we've got dozens of encoded files for every upload. Where does all of that actually sit? Not in a normal database. The raw video bytes live in Google's planet scale file system called Colossus. And planet scale isn't a figure of speech. A single one of these clusters holds exabytes, billions of gigabytes, and reads data back at over 50 terabytes every second. But storing this much comes with a quiet problem. You can't just make 3 copies of everything. So instead, Colossus uses erasure coding, splitting data with just enough mathematical redundancy that it survives disks failing, but only costs about 1.5 times the space instead of 3. And it's smart about heat. The video everyone's watching right now sits on fast flash, while the clip nobody's opened in years drifts down onto cheaper, slower disk. Here's something people get wrong about big systems. They assume there's one giant database running everything. There isn't. YouTube uses different stores for different kinds of data on purpose. The video files live in Colossus. The details, title, channel description live in a sharded MySQL setup. The fast-moving counters and history live in Bigtable, which handles over 6 billion requests a second across more than 10 exabytes. And the money, ads, payments, sits in Spanner, the one store built to be globally, probably correct. And that metadata store has a great backstory. Early YouTube ran on ordinary MySQL, and as it exploded, that database started buckling. The usual advice would be to throw it out. YouTube did the opposite. They kept MySQL and built a layer around it called Vitess that splits the data across thousands of machines while making them all look like one normal database. That trick let YouTube grow more than 50-fold on the same familiar foundation. And here's a puzzle hiding in plain sight. How do you count views? Sounds trivial. It is absolutely not. Views arrive from everywhere on earth at once. Bots try to fake them. And you cannot stop to take a global lock every single time someone presses play. So YouTube counts approximately, fast, and then reconciles the real number later after checking for fraud. For years, this produced a famous quirk. Popular videos would freeze at exactly 301 views, stuck there while the system verified the flood behind the scenes, then suddenly jump. And there's an even better story. When Gangnam Style blew past 2 billion views, it overflowed the counter itself. The number was stored in a slot that couldn't hold a value that big. YouTube had to widen it from 32 bits to 64. The public view count, it turns out, was never meant to be exact. Okay, the video is uploaded, transcoded and stored. Now the other half of the machine wakes up, getting it to viewers. And the delivery has the same chop it into pieces instinct as the encoding did. Each version isn't served as one long file. It's sliced into short segments just a few seconds each, with a little index file, a manifest, listing every quality level like a menu. And here's where it gets smart, because the video comes in little segments and every segment exists at every quality. Your player gets to choose, segment by segment, which quality to grab next based on how your connection is holding up right now. That's why on a patchy connection, YouTube almost always starts a little blurry and then sharpens. It's not being cheap, it's starting low. So playback begins instantly, then climbing once your buffer proves the connection can take it. Now the biggest trick of all, and it's the reason YouTube feels instant even though the video might physically live in another country. Remember that 1000-to-1 ratio. You solve it by not shipping the same popular video across the world a million separate times. Instead, Google places its own cache boxes physically inside your internet provider's network, inside Jio, inside Airtel. So when a video is popular in your city, a copy is already sitting a few kilometers away, and it never has to travel the long distance internet at all. Google says these in-network caches serve somewhere between 70 and 90% of the cacheable traffic locally, across over 1300 cities. The video didn't come to you from California, it came from down the road. And the edge acts like a popularity filter. The trending song is pinned close. The obscure clip from 2009 lives deeper and takes just a moment longer to start. So far, everything's been about one video's journey. But with hundreds of millions of videos, how do you even find one? Search starts with your words. You type a query and the system matches it against the title, the description, the tags, and even the spoken words inside videos, transcribed automatically. Then it ranks what matches by 4 things YouTube actually names: how relevant it is, how much other people searching that same thing chose to watch it, how trustworthy the channel is, and your own history. Search answers a question you asked out loud. Recommendations answer a question you never even said. Recommendations are where YouTube gets almost spooky, and the engineering is genuinely beautiful. The problem is absurd on its face. Out of billions of videos, pick the few this exact person wants next and do it in a few tens of milliseconds while they wait. You can't score billions of videos in that time. So YouTube splits it into 2 stages. First, a cheap fast pass called candidate generation narrows billions down to a few hundred. Then a richer pass, ranking man, carefully orders just those. And that first pass has a lovely shortcut. YouTube turns every video into a string of numbers on an embedding that captures what it's about, does the same for you based on everything you've watched, and now what should you watch becomes a geometry question. Find the video points sitting closest to the U point, pre-computed ahead of time, so it just looks up your nearest neighbors in the blink of an eye. And now the single most important idea in this whole system. When YouTube ranks those candidates, what is it actually optimizing for? The obvious answer is clicks. And that is exactly the trap. If you optimize for clicks, you get clickbait, lurid thumbnails, lying titles, videos people tap and then immediately abandon. So, YouTube made a different choice. It ranks by watch time. Not did you click, but did you stay? A click can be a lie. The minutes you actually give a video are the truth. When YouTube's own engineers tested removing that idea, their model got measurably worse. And the newer ranker juggles more than watch time. Did you like it? Share it? Come back. And even corrects for the fact that people click the top result just because it's on top. Now remember, 500 hours a minute are pouring in, and some of that is copyrighted. A song, a movie clip, a match broadcast. YouTube can't have humans watch all of it. So it built a machine that does, called Content ID. When a rights holder registers something, YouTube reduces it to a fingerprint. A compact signature of that exact audio and video, robust enough to survive re-recording, speeding up, cropping. Then every single upload gets fingerprinted too and matched against that reference library in near real time. When it finds a match, the owner chooses block the video or leave it up and take the ad money instead. And most choose the money. This system has paid rights holders over $12 billion, handles more than 2 billion claims a year, and does over 99% of it with no human in the loop at all. For the truly premium stuff, a movie you rented, a downloaded premium track, a plain fingerprint isn't enough. The actual bytes have to be locked. That's DRM, and Google's is called Widevine. Here's the strange, clever heart of it. Your device decrypts the movie without ever being allowed to look at it. The decryption happens inside a sealed hardware vault that the rest of your computer, even the browser, can't peek into. And there are levels. A phone with that secure hardware gets full HD. A regular desktop browser, which only does it in software, gets capped at standard definition. That's the real reason the same film looks sharper on your phone than in your laptop's browser. And one last log. Every playback link is a ticket that self-destructs, signed, stamped with a short expiry, and dead by the time anyone can copy and paste it. We built the whole machine now. So let's ask the scary question. What happens when part of it breaks? And at this scale, something is always breaking. Disks die by the hundreds. Whole data centers get pulled offline for maintenance on an ordinary Tuesday. YouTube's answer is to treat failure not as an emergency, but as the normal weather. Traffic is spread across many machines by a load balancer. Google's is called maglev, and when a machine or a whole region goes down, the system reroutes around it, keeping your video playing on a connection that's quietly moved to a healthy part of the world, without you ever noticing the switch. And when it genuinely can't keep up, when the load is just too much, YouTube does something disciplined. It doesn't crash. It degrades, it quietly drops you to a lower resolution, holds back the fancy sidebar, defers the least important work, and keeps the one thing that matters running. The video keeps playing. That's the whole philosophy of this system in one line. At this scale, you can't promise nothing will break. So you promise that when it does, the picture might get a little softer, but it never goes black. So that's the machine. One creator in Mumbai hits upload, and that single file gets sliced, exploded into dozens of versions on custom silicon, scattered across a planet-scale file system, counted approximately, matched against a copyright galaxy, locked, indexed, ranked by the minutes. You'll actually give it, and finally served to you from a box sitting inside your own internet provider. 500 hours every minute in. 1,000 times more back out, write once, read a billion times. That's not one clever idea. It's the same idea echoing through every layer. Next time, we take on the hardest version of this problem there is. Not a stored video, but a live one. 25 million people, one cricket final, all pressing play in the very same second. See you then.